two of our two new future colleagues who will join the department in September. We're very happy about that. And Xin took his PhD from Berkeley 2 years ago, from Michigan, Michigan, 2 years ago. That was very young. So Xin from Michigan with Erhan.
Yeah.
And since then, you're postdoc in Vienna in the group of Matthias Feigelbach.
Yeah.
And you have been working on optimal transport. And this is the subject that you've chosen to talk about today, although it's very abstract, but I'm sure you will make it
I will try to make it
for this audience. Thank you very much, Xin.
Thank you. Perhaps I should start sharing. Thank you for your introduction, and I feel very excited to join you this fall. Today, the topic is the Wasserstein space of stochastic processes. It's based on the joint work with my colleagues in Vienna, Danny Bartel, Matthias Gudmund, and Stefan. So here is an overview of this talk. In the first part, I want to briefly mention the motivation and the central question we want to understand. And then I would like to introduce the main result. In the second part, I want to explain you what is the optimal transport problem, which was introduced in March. And this optimal transport problem defines the metric between probability measures. And then I want to introduce an adapted version of optimal transport, which defines distance between stochastic processes, and that can be used to quantify differences of models, okay, in mathematical finance. So a central question in math finance is to understand how do decisions perform if reality deviates from the underlying modeling assumption. Okay. We usually model our stock price by stochastic processes. And the stochastic process is a sequence of random variables ordered in time. However, in any modeling practice, we have the issue of model uncertainty, which means that no model can characterize reality with perfect accuracy. So suppose we design a trading strategy under some modeling assumption. We hope this strategy still performs well, even if the reality deviates from our modeling. Okay. And to understand this problem or analyze this problem rigorously, we need to know how to quantify the differences between model and the reality. However, there is no systematic study on this topic in the continuous time case because there is no proper distance between stochastic processes. A crucial feature in math finance or stochastic process is the availability of information at each moment of time and the evolution of information. Okay. So for example, on stock market, people with more inside information can make more money. And so in math finance, the information structure is quite important. And in this talk, we want to design a metric or a distance between stochastic processes that captures the evolution of information for stochastic process. Okay, and a stochastic process can be identified with two parts. First is the probability distribution on the path space. Okay. And the second one is the information structure or the filtration of stochastic process. Therefore, to understand the set of stochastic processes, let's first take a look at the set of probability distributions or the probability measures. And here, topology is the underlying structure of a set. And with topology, we can talk about neighborhoods of points and continuity of maps. And on the set of probability measures, canonical topology is the so-called weak topology. It's the weakest topology that makes the integration of functions continuous. Therefore, it's a natural choice when studying the convergence of probability measures. And besides that, for weak topology, we have the so-called Prokhorov theorem. Therefore, we can easily characterize the pre-compact sets. And it's quite convenient for optimization problems. And it turns out that this canonical topology is matroized by the so-called Wasserstein distance in the theory of optimal transport. Okay. Optimal transport was proposed by Monge in 1781. And this problem asks how to transfer a probability measure to another one in the most efficient way. Okay. Since then, it has become a classical object in probability. In the last 40 years, it has gained popularity due to its connection between partial differential equation, geometry function analysis, and probability theory. And two Fields medals were awarded to Filani and Figali for their contributions. Okay. And recently, the optimal transport theory has become a fundamental tool in machine learning and image processing. It's because we can always identify data sets as probability distributions. And then optimal transport can be used to define a distance or difference between data sets. Okay, now let's turn to the set of stochastic processes. Different researchers have been interested in the topology on the set of stochastic processes for a while, and they strengthened the usual weak topology so that different kinds of stochastic properties are continuous. I will show you some examples later on. And we call that topology adapted weak topology. And it's stronger than the weak topology. Okay, so as I said, different researchers defined topologies for different reasons. And with my colleagues in Vienna, we proved that all these topologies are equal and they are matroized by this adaptive Wasserstein distance. Okay. In particular, we show that Alder's extended weak topology, Hellwig's information topology, Hoover-Kissel topology, and information topology for optimal stopping, they are equal on the set of continuous time stochastic processes. Okay. I will explain in more details about these topologies later on. Okay. The main result is that all these topologies are equal, and we constructed an adaptive Wasserstein distance that matroizes all these topologies. Any questions so far? Yeah, continuous time and discrete time. Yeah.
Is there take it to extend, you've got two processes that are close, effectively Wasserstein distance. If I look at basically for the range of 6 meters d, there's two densities, right? I mean, I think of it in terms of the two densities give roughly similar probabilities for each little, you know, like the average. I mean, is that a constructive way to talk about being closer to what we're saying of the stochastic processes?
That's a great point. We will give an example later. So what you said is the Wasserstein distance between the density or distribution of these two stochastic processes, right?
Right. All these are, but all future time.
Yes, yes. But we will show that it's not a good way to define distance between stochastic processes because it ignores the information structure. Okay. Thank you. Okay, so let me first explain what is the optimal transport problem. Here are two special cases. This is the example from Villani. Every morning in New York, bread must be transported from bakeries to cafes for consumption. And these bakeries and cafes, they are at different locations, blue dots and red dots. We assume that each bakery, they produce prescribed amount of bread, and each cafe consumes a prescribed amount of bread. And also the transport cost of one bread from bakery to cafe depends only on the transport distance. Okay. Then we are looking for the most economical way to distribute bread. Okay. And this is actually a linear programming problem. And I want to emphasize that in this example, we can view bakeries as a probability distribution and cafes as a probability distribution. So the probability mass of this blue dot is the proportion of bread it produces. And the probability mass of this red dot is the proportion of bread it orders. So in this problem, we are actually looking for the most economical way to transport the distribution of bakeries to the distribution of cafes. This is the second example. Suppose on the left, we have a pile of sand with distribution F. F is the density of this distribution. And on the right, we have a hole with distribution G that we want to fill up with the pile. Then the movement of each particle can be modeled by a map T, which transfers particle at position X to Tx in the hole. And then we are looking for the most efficient way to fill up the hole with the pile. We can show that if the transport map T transfers the distribution F to distribution G, then it satisfies this first order equation. Okay. And in the optimal case, by Brennier's theorem, the optimal map is gradient of some convex function. Therefore, this equation induces a second order equation. It's known as Monge-Ampère equation. Okay. In the general case, for a probability measure P and a map T, we can define its push-forward measure. Where is the mouse? So here you cannot see it, but it's a TP equal to Q. It's here. Okay. And in the Monge problem, we are interested in the most efficient way to transfer P to Q. Okay. And here Tx minus X is the transport distance of particle X under the map T. Okay. This problem looks simple, however, it's quite hard to solve due to the non-convexity of this transport constraint. Okay. So in 1940, Kantorovich relaxed this problem. Instead of transport maps, he considered couplings between probability distributions and therefore made this problem convex. Okay. So next. How you want to change slide? Yeah, I want to change slide. Yeah. Okay. Okay, here. So then the Wasserstein distance between P and Q is the minimum transport cost among all couplings between P and Q. Okay. And it can be shown that when the probability measure P is absolutely continuous, the Monge problem is equivalent to the Kantorovich problem. Okay. Although the concept of coupling is quite common now, it was a breakthrough at that time. And Kantorovich got Nobel Prize for economics due to his contribution in linear programming and resource allocation. Equipped with the Wasserstein distance, the set of probability measures is the so-called Wasserstein space. And people have shown that this Wasserstein space has many geometric properties. So this is a brief introduction to optimal transport. And in this talk, we will only talk about the transport map T. And I don't want to distract you by the concept of couplings. Okay. So.
Right? You simply mean there's a random variable on the left-hand side. So the function T is going to get the distribution of T of n variable is the distribution of U.
Yes.
By that statement.
Yes, exactly.
Standard notion of applying a function.
Yeah, push forward. Yeah. Yeah.
So that's a condition on T. You're looking for the T that solves that? This is the condition.
Yes, P and Q, they are fixed, and we are looking for T that minimize this transport cost.
What T is identity function?
Then P, T's identity means P is equal to Q.
Right.
So for,
given, okay.
Yeah, they are given. Yes, yes, yes. And this is the transport cost. Okay. So now let's turn to processes. Here, the x-axis represents time of process, and the y-axis represents the value. Okay. Here we have two stochastic processes. The left one, it has two paths, one upward, one downward, each with probability 1/2. Okay. And we can see that these two paths, they coincide up to time 1. And then at time 1, they branch into two directions. The process on the right is almost the same as the process on the left. The only difference is that the two paths, they diverge from time 0. Okay. So the first thing is that these two stochastic processes, they have very similar probability distribution. Okay. To see this point, the upward path on the left is almost the same as the upward path on the right. And the downward path is similar to the downward path on the right. So the transport map that transfers upward to upward, downward to downward, actually yields very small transport cost. So the Wasserstein distance between these two distributions is very small. However, these two processes, they have very different information structure. Okay? And for the process on the left, these two paths, they coincide up to time 1. So if we observe this process until time 1, we cannot know its value at time 2. It's random, right? It can either move upward or downward with probability 1/2, given the information up to time 1. However, for the process on the right, if we are given its value at time 1, its value at time 2 is deterministic. Because if we add this point at time 1, at time 2, it will move deterministically upward. Okay. And if we consider these two processes as a stock price, then the process on the left says that given today's stock price, tomorrow's stock price is random. Okay. But the right one means that if we're given the stock price at time 1, the stock price at time 2 is deterministic. So that's a huge difference. Okay. And this difference in the information structure has big impact in the stochastic optimization problems, such as optimal investment, utility maximization, and optimal stopping. Okay. So it can be seen that the optimal stopping value of this process is quite different from the right one, because for the right one, we can distinguish these two paths from time 0. Okay. And this example, from this example, we can see, although these two processes, they have very similar probability distribution, they are actually very different as stochastic processes. Okay. So in the following, we want to construct a metric that captures their information structure. Okay. So first, I want to define adapted Wasserstein distance in the discrete time, and then I will introduce the construction in continuous time. Here is our setup. We have a stochastic process X. Here, X1 is its value at time 1, and Xn is its value at time n. Okay. For processes with n time step, it can be identified with a probability distribution on Rn. And here, n is not the dimensionality of X. It should be interpreted as the time horizon of process. Okay. And suppose we have two processes, X and Y, with distribution P and Q respectively. And now we want to define a distance between X and Y. Here is the usual Wasserstein distance. And first, I want to give a probability interpretation of this constraint. Okay. A transport map T now is from Rn to Rn. Okay. And we can write T in coordinates. So T1 is the value of T at time 1, T2 is the value of T at time 2, and so on. Okay. Now we know X, it's a process with distribution P, right? And we have this transport constraint, Tp is Q. So the random vector on the left should have probability distribution Q due to this transport constraint, Tp is Q, right? Okay. So the left and the right, they should have the same probability distribution. Good. And in the setup of stochastic processes, now the index represents time. So at time 1, we only observe the process up to time 1. So the transport map T1 can only be a function of X1 only. And at time 2, we observe the process up to time 2. So we have the information generated by X1, X2. So the transport map is a function of X1, X2 only, and so on. And this is the so-called adapted constraint, which means that at each moment of time, our transport map can only be a function of past information. Okay. So with this additional constraint, we can define adaptive Wasserstein distance in this hand-waving way. So, but for an official definition, we need to transfer this adaptive constraint to the set of couplings and symmetrize this constraint. We want adapted from P to Q and also from Q to P. Okay. And this we can show that it gives rise to a metric. And this metric can be used to study the stability result with respect to underlying models. In discrete time, many people have contributed to this topic, such as Bear, Julio, Benny Bartle, Matthias, and so on. Okay. And now we are interested in the distance in the continuous time case.
Suppose for T2, I require the conditional RS1 T2 matrix Y2 conditional Y1. Does it make any sense? This type of when you say adapted, or like conditional on the past history, then the current same matrix, the object or the target. So I want to add that can I also impose this conditional function away.
That's a great question. I think, yes, actually. Yeah. You want to match the conditional distribution of of x2 given x1 to the conditional distribution. Okay, I think actually these two questions perhaps we can show their equivalent, but the point is then t is a function from distribution to distribution, and it makes this problem more complicated. Okay. Yeah. 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 Yes. As I said here, it's a heuristic way to define this metric. We need to transfer this adaptedness condition to couplings, but I don't want to distract you. Yeah, so for coupling, you can easily discuss causal from one to the other. Do I answer your question? So actually, we need, you are right, we need adapted from one P to Q and also from adapted from Q to P. Okay, now let's move to continuous time case. Here, a stochastic process xt, it can be identified with a probability distribution on the continuous path space. And we want to define a metric between P and Q on this C01R. A very straightforward extension is the following. So we can define here T is a function from path space to path space. And we say T is adapted if at each moment little t, our transport map is a function of the past path. So here, this notation x0t is the path of x up to time little t. Okay. It's a straightforward extension of the discrete time case. And it can be shown that this definition actually is a good one between regular stochastic differential equations. Okay. Lipschitz of the coefficients. Yeah. Yeah, and under some under other mild conditions, they obtain the optimal coupling between SDEs. Okay, but I will show two examples that suggest that this definition is not ideal for general stochastic processes, not SDEs. Okay, the first one is Danska's theorem, which says that the distribution of random walk converges to the distribution of Brownian motion. Okay. And this Danska's theorem is quite important in stochastic analysis, and it's a functional central limit theorem. So we hope we have the convergence from random walk to this Brownian motion, not in weak topology, but also in our adaptive Wasserstein distance. So we hope for a stronger convergence result. So that means we have random walk close to Brownian motion, not only as distributions, but also as stochastic processes. Okay. And the second one is this example. We come back to this picture again. So it's a stochastic process with two paths. Each path has probability 1/2. Okay. The process on the right is almost the same as the left one. And the only difference is that the two paths on the right, they diverge at time 1.1 instead of at 0.1. Okay. And we hope these two processes are similar to each other because physically we cannot measure time with perfect accuracy. So we cannot make a big difference between information arriving at time 1 and the same information arriving at time 1.0001. Okay. So the right process on the right is a shift of the process on the left in time. Okay, and we hope these two should be very close as stochastic processes. However, we can show that there are only trivial adapted maps from random walk to Brownian motion, and trivial adapted maps from the process on the left to the process on the right. Let me try to explain this point. So for random walks, its paths are piecewise constant. So its information filtration is like a jump function, right? However, the filtration of Brownian motion involves continuously, and it's hard for us to match jump process to a continuous time increasing process bijectively. Okay. That's why we only have trivial adapted maps from random walk to Brownian motion. Okay.
I don't understand the term. What do you mean by trivial adapted?
So here I say it in maps, but if you consider in the case of coupling, that means the only bicausal coupling or adapted couplings between random walk to Brownian motion is the product coupling. So it's yeah, it means it's a product coupling, which means no matter which is your path, you assign this path equally to the path on the right. Does it make sense? Uniformly. No, send the upward one with probability 1/2 to upward and right, upward and downward. That, yeah, there's no dependence. They are independent. Absolutely, yeah, completely independent. So if you, yeah, it suggests that if we define a distance using the definition in the last slide, then we will not have the convergence of random walk to Brownian motion, and this process is very far away from the right one, no matter how close they are. Is everything clear? So all I want to say is the definition, definite constraint on the last slide is not good enough. Okay. Or if you take a look at this process at time 1, we cannot distinguish these two paths, right? So how can you transfer the process on the left to the right if you impose the definite constraint? The only way is we randomly choose a path.
But in the sense of the Wasserstein metric, it's a big distance, right? So topology is close, but the metric is not small.
Yes, if we define the metric as in the last slide, yeah, they are not close. Yeah, that's what I mean. Yeah, we need to modify the definition on the last slide. Yeah, thank you. And and from the examples, we can see the main problem is we need some flexibility in the information structure. So we want to allow our information or the filtration to wiggle in time. That's why we define this epsilon-adapted constraint. And here it means that at each moment of time, the transport map T at little t is a function of x up to time t plus epsilon. So before, it's a function of x0 t. Okay. So here, this epsilon should be interpreted as the weakness in time. We don't make a big difference between time t and time t plus epsilon. Yes. Yes. No. We also allow CATLAG. Yes, it works also for CATLAG. Yeah. Yeah. And then we define adaptive Wasserstein distance using this epsilon-adapted constraint. Okay. Here we plus epsilon to penalize the wiggling time. We can show that with this formal definition. This adaptive Wasserstein distance is this definition. This gives rise to a distance, and it has many nice properties. Okay, the first one is the convergence of random work. We want to show random work are close to Brownian motion as stochastic processes. The key ingredient argument is this compactness criteria. Okay. We prove that a set of stochastic processes is pre-compact in this adaptive Wasserstein distance if it's pre-compact in weak topology. And so this is a much more complicated metric than the Wasserstein metric, but we can show the compactness is equivalent with back to these two concepts. So this one is if we have a sequence that converges in the AW, then it should converges in W. But the other way is also correct in up to some. Yes. Okay. So the topology induces by this adaptive Wasserstein distance is much stronger than this weak topology, but we're able to show that the pre-compact sets are somehow equivalent. And with this compactness criteria, we can give a brief argument to the Danska's theorem. First, by classical Danska's theorem, we know that we have the convergence of random walk in weak topology. Therefore, the distribution of random walk is pre-compact in weak topology, right? And then thanks to this lemma, it's also pre-compact as processes with back to this adaptive Wasserstein distance. So we have a limit point. Okay. Second, we can show that the property of being martingale is preserved by adaptive Wasserstein distance. And then because a scaled random works, they are martingales, the limit point must be a martingale as well. So the limit point is a martingale with Brownian distribution. Okay. And in the end, by stochastic analysis, we know martingale with Brownian distribution is Brownian motion by Levis characterization. So we conclude that any limit point must be a Brownian motion, therefore conclude the result. So this is one application of this compactness lemma. We will give another one later. What's the time? Okay. And here are some stability results of this metric. First, we can show that Euler schemes of SDE converges. Here ST is BST, BT plus a sigma ST dBT. And we can define its Euler scheme as Sn, which distribution is denoted by Pn. And we show that the adaptive Wasserstein distance between Pn and P is given by, is bounded from above by log n over square root of n. So as n goes to infinity, Pn is close to P. Okay. The second one is the continuity of optimal stopping. So suppose we have a stock whose price is modeled by a distribution P. Okay. Then we want to sell our stock at the best time so as to maximize our payoff. Here, phi, x, tau, and tau is the payoff if we sell our stock at time tau and at price x tau. Okay. So we want to maximize the expectation among all the stopping times. Clearly, this optimal stopping value is functional of our distribution P. And we show that this optimal stopping value is Lipschitz continuous with back to P under some mild conditions. And the idea is that using the adapted transport map, we can transfer stopping time of one process to another one. Okay. Now let me give the main result. So many researchers have strengthened the weak topology so that some stochastic properties are continuous. Elders first observed that the optimal stopping value we presented on the last slide is not continuous with back to the usual weak topology. So he defined the so-called prediction process and the extended weak topology so that optimal stopping values are continuous. For any probability distribution P on the path space, okay, we define its prediction process to be the conditional distribution of X given path information. Okay. So therefore, we get a process on a complicated space on the set of probability measures. Okay. So for phi, it maps P to its prediction process defined here. And then the extended weak topology is the weakest topology so that phi is continuous. Okay. Here we equip a set of prediction process with the weak topology. Okay. So it's on the right-hand side, we have weak topology on a more complicated space. And we define the extended weak topology as the weakest topology such that phi is continuous. Make sense? Okay. And also Helwig defined the information topology so that dynamic games are continuous. And the idea is very similar. We, at each moment of time, little t, we disintegrate future with back to our past information and define this map per psi t. Okay. Then the information topology is the initial topology with back to per psi t for t in 0, 1. Okay. And the third one is Hoover-Kissler topology. It guarantees the continuity of all probability operations, including taking iterative conditional distributions. And the fourth one is the initial topology of optimal stopping. We want the optimal stopping values are continuous with back to our process. Okay. Okay. And we prove that all these topologies agree on the set of continuous processes and they are metrized by the adaptive Wasserstein distance we defined. Okay, and here is perhaps we skip this part. So in the end, let me mention a technical result, the completion of space. Let's go back to this picture again. This process has two paths, one upward, one downward, each with probability 1/2. And at time 1, the distance between these two paths are indexed by epsilon. Okay. So this epsilon denotes the distance between these two paths at time 1. And we can see that for any positive small epsilon, these processes, they have similar, the same information structure, right? And similar distribution. So we have a Cauchy sequence in this adaptive Wasserstein distance. And we are wondering what could be a limit point, okay? It turns out that our adaptive Wasserstein distance is stronger than the Wasserstein distance. So the limit point must have the distribution of this process. Okay. probability 1/2 of upward path and probability 1/2 of the downward path. However, because for the processes on the left, we can distinguish these two paths from time zero. So for the limit point, the limiting process should be able to distinguish these two paths from time zero as well. Okay. That means the information structure or the filtration of the limiting process is not generated by the path, because for the process on the right, we cannot distinguish these two paths from time until time 1. However, as a limit of the process on the left, we should be able to distinguish from beginning. And in the stochastic analysis, we have the notion of filtered process, which allows us to define processes on a general probability space and general filtration. Okay. And we prove that the completion of this space, okay, is the set of filtered processes. Okay. So yeah, it implies that our notion of adaptive Wasserstein distance is a good one. Okay. And in the end, I want to mention some interesting open problems. The theory of optimal transport studies the set of probability measures, and we are interested in the set of stochastic processes. And the optimal transport theory provides a blueprint for our research. We already see that our adaptive Wasserstein distance has nice topological properties. It matrices all adaptive weak topology. However, it's not a geodesic metric due to the epsilon wiggling time. By geodesic, we mean we can find the minimization curve between any 2 points. Okay. And therefore, I'm wondering if we can find a metric which is more geometric. And the second one, in optimal transport, we know that the gradient flow of entropy with back to Wasserstein distance is Fokker-Planck equation. In the setup of the stochastic process, we have specific relative entropy and adaptive Wasserstein distance. So it would be nice if we can find the gradient flow of specific relative entropy with back to adaptive Wasserstein distance. And here, the key point is to understand the tangent structure. Okay. The third point, so until now, there are many results about stability analysis. However, little is known about its computation and statistical properties. It would be great if we can compute adaptive Wasserstein distance efficiently. And in the end, I think this adaptive Wasserstein distance can be used in ending a stability analysis with back to underlying models. And I hope to find more applications in stochastic control problem and finance. And that's it. Thanks for your attention. Any questions?
Go back to the epsilon part. What's it about epsilon? It has to be positive?
Yeah, it has to be positive. Yeah.
This is ahead of I wonder what would happen if you say T minus epsilon? I mean, is there anything would be break down those things?
Yeah. You restrict epsilon to be negative, or you allow epsilon to be negative.
Allow.
Okay. In the end, I think He yeah. If you restrict epsilon to be negative, then perhaps it's not good for our purpose, because as already shown by these two examples.
That would be 0.9. Otherwise, it would be 0.9.
Yeah, it doesn't matter from 1 to 1.1. We want ending point close to 1. They are close to each other. So it's better to give a more general, more relaxed definition instead of restricted definition.
Associate conditional law in F1. In the sense of the topology that's singular, that's not continuous. What about in
AW? Conditioning then. You mean this prediction process? This one, right? Are you talking about this one?
That's not the law of the law. I just think I associate with the law of X.
Yeah.
Is that continuous under AW?
No, that's how we define AW.
We define AW as most topology which make it not continuous, right?
Oh yes, that's how we define AW. Yes. Yes.
Sort of in the middle, talks about ending the number of time steps. Let me go back a little bit, a little more.
Yeah. Yeah. This
so
one.
In other words, so this is like, so and I think of x1 to xn as being the distribution of the process at different discrete times. That's what it is, right? So a point in this Rn is a vector of distribution. Am I correct in saying that? When you write x1 to xn, those are random variables. Those are random variables, right?
Yes.
Okay, so a point in this Rn is a vector time direction density function.
Yeah.
Right.
So there are two ways to interpret this index, right? One, so as processes, the index represents time, but you can also interpret.
Okay.
Yeah.
So then this measure dx, right, in the formula for the distance, right? The dx. That's a measure in this space of
Rn.
But Rn, it's not Rn, it's not Euclidean space. Each point in it is a vector of random density function. You know what it's
No. It's really on Rn, and
You can.
what we denote x1 is the projection coordinate on this. So it's the map from Rn to R, which maps each vector.
Okay.
Then to x1, first coordinate.
Okay.
x2, second
Yeah.
coordinate.
Right.
So these are maps from Rn to Rn. No coordinate. No density.
But so the x1 to xn is not a vector of random variables. It's not.
Vector of map.
There's just a point. Just so the point, the element of an Rn is simply a point including in the dimensional space.
Yeah. Yeah, and the P is the distribution of X, joint distribution of this X1, X2, and Xn.
I thought that. Okay, thank you. I'll think about it. Thanks.
So even the Gaussian, that's a law on R.
Yes, correct.
You take the two-dimensional Gaussian, that's a law on
R2.
Correct.
Yes.
N-dimensional Gaussian is a law on Rn. But
Right.
we can have other laws.
Yes.
P and Q. And
Correct.
then we want to map the law to a map.
Yeah, I certainly understand that. So it's not like, I was thinking, but n is the time, n is discrete time. N is a discrete time.
Mm.
Right, one to n.
Yeah.
Right? So I thought the xi's were themselves the random variable representing the value of the process at different points in time. Doris saying, no, it's simply regular Euclidean, xn, projection map. Xi projection map to.
And then you can put this distribution on that.
Yes, of course. Understood. Thank you.
Very quick question.
Hmm?
So the key aspect of defining new Wasserstein distances is the topology and playing with some topology and really defining weak topology and relative topology.
Mm.
This unique, maybe not. I mean, playing with topology is not unique. And there is sometimes pair by definity with the vector space. So can you like have different like outcomes, different like distances from weak topology?
It depends on your purpose, what properties you want from this metric.
So what do you
You can define other things, but it may not have the property we want. So here for stochastic processes, we want certain continuity property of stochastic maximization problems. Yeah. Thank you. Thank you.
Yeah. Mean field gains with common noise.
Mm.
The first paper who was doing that is the Carmona and Lacker, I think.
Yeah.
And there is a very involved proof to establish the existence of a fixed point. And and the technical difficulty